Welcome back to the Fullerton College Pre-Press lecture. This is Professor Ben Hewitt. We're carrying on in our PIA manual today, section 4.3 Digital Image Basics. And now we are going to look at lab color space, also known as CIELAB, which is spelled C-I-E, and that's an acronym and it's in French. We'll get there in a moment. This is a very interesting one for me and something that I am quite happy to talk to you about. No, it may end up being its own video, and I'm very sorry if this ends up being a very slow week because of this, but this is an important topic. Lab color is a visual color model that uses three components to describe a color. The L in lab stands for luminance. I told you it was French, right? That's not something you'd probably say in English as the way you'd want to describe it. But the L is for how bright or dark it is. It's light to dark. We would probably just call it lightness. That would be more of a, especially American English version of luminance. Luminance. Yes, how about lightness, guys? So how light to dark it is. That doesn't take much explanation since we're pretty adept at understanding what a bright color is and what a dark color is. We all know the difference between black and white, and it's very obvious to our eyes. The other ones, the A and the B, talk about two axes if you're making this into a graph or a map. The picture on the right is a pretty accurate depiction of what it is trying to do, although the exact shape is not precisely a sphere, really, if you actually mapped it out. So you have these pairs of opposite colors, green or kind of magenta red, and blue or yellow. So A is how red or green it is, and B is blue or yellow it is. If this looks kind of like a sphere, globe, I was going to say sphere. Well, yeah, it's a sphere. If this looks kind of like a globe, that's kind of the idea. This is using this is a three-dimensional graph mapping out where colors are in relation to each other. If you want to get into it, what is this thing? Why, this is in fact a map of human color perception. This is everything the average human eye can sense and the differences that we see as we see it. So this is a chart of human perception, and it is really, really cool. Oop, button to push here. So that's why these things are opposites, because to us as people, when we see blue, we're also not seeing yellow. When we see red, we're also not seeing green. Those are kind of opposed colors, complementary colors, you might call them in an art mixing sense. But in the more psychological sense of what are we seeing, what are we mapping, those seem to be how we see. So we'll go into this a little more here. The C in CIELAB, CIE, is the French think tank. And I'm going to butcher this because I don't actually speak French. The Commission Internationale de l'Éclairage, or the International Commission of Lighting. And this is coming up with the ideas of a standard observer, something called delta E, which is a frat I'm going to start one of these days, I swear. And then the CIELAB and CXYZ color spaces are all things they've come up with. So let's jump in more. Oh, actually, we didn't jump in enough. Honestly, this thing needs a little more attention than the 2 slides they give it. So I think we'll talk about it more in the future, but delta E is talking about differences between perceived colors. And I'm not going to go into too much detail because we do circle back to this in a future week, but just understand that this is a chart. This is a map of all the colors you can see, and delta E is simply the distance between 2 points in the map. Remember that, or I don't know about remember, if any of you have taken classes in physics, you understand delta, the Greek letter delta, to mean change in most science. In physics, you're always working with delta V, which is change in velocity, or something like that. Change, how much energy is in it. For us, E is a lowercase e for the delta E means it's a German word, which I don't have on the top of my head, but it's a change in sensation. So how much of a visual difference is there between these 2 colors? It's an important concept for trying to figure out how close things can be. But again, I'm getting ahead of ourselves on that. So let me switch over to my other chart here. Here's my version of the lab color. It's not exactly my version. Hat tip to Don Hutch. from ID Alliance and Hutch Color, who came up with this as a part of his G7 training that I've gone through. So again, you don't need a whole lot of help remembering positive or negative L. L is 0 to 100. 0 is black, 100 is white. And that's how bright or dark the color is. The A and the B, just to help you understand that the positive and negative are not better or worse. They're not even exactly more or less. They're locations on a graph where 0, if you go 0, 0, 0, 0, 0, that's the center of the graph and all the way dark. If you have an A star and B star of 0, you're talking neutral. Whether it's black, gray, or white, it's neutral. And that is what that is. A negative A means it's leaning green. Positive A, it's leaning red. Positive B is leaning yellow. And negative B is leaning blue. Here's how to remember that. Remember. Let's go with the B. It's easier. Banana starts with B, and it is big. So bigger B numbers are yellow, like bananas. Smaller things that start with B are blueberries, and they're blue. So negative B is blueberries, is blue. A negative B for an LAB value means it's going to be leaning towards the bluish side. But then you have to go for the A. A is for apple. Red apples are better than green apples. So red apples are positive A, and negative is green apples because, unless you're baking a pie, who wants those? We'll jump back over here. So that was the lab color space. A big difference between this and other color spaces is lab color space is not NOT, not trying to reproduce color. RGB, grayscale, CMYK, index color, duotones, those are all those are color reproduction models. Those are ways of approximating color to try and create it, to show it to you. Lab would be impossible to create without creating the world itself. Lab does not attempt to create anything. Lab is, like I was saying, it's a map. It's a chart of what we see. Lab contains all of the possible colors the human eye can be sensitive to, on average. Obviously, there's no such thing as completeness in science. There's always some weird, freakish outlier. Maybe somebody has the ability to see more colors. The average human can see all these colors. And that is a much wider gamut, way more colors possible than any of the other ones so far shown. And so far, there's no system that does lab color truly does it. It's something you can record, but not something you can reproduce. So let's talk resolution. Image resolution is talking about how many pixels do you have. More pixels is good. Less pixels is not as good. The terms you might hear are DPI and PPI, which are kind of interchangeable. They mean dots or pixels per inch. High res, low res, and file size are also part of the equation and part of what people talk about. High resolution is typically good. Low resolution is typically bad if you're talking about printing. And file size is an interesting way of kind of judging without looking too closely at what kind of resolution you're going to have, although it's not a 100% accurate way to judge it. So resolution of a digital image is best determined before you scan. You need to make sure you have enough pixels to make this work. If you don't have enough pixels, you get a jagged image, and it looks like it's made out of Legos, and I don't mean that in a good way. You can see those bricks that build up the picture. You shouldn't be seeing those. It's like when you look too closely at it, you see all the edges. Too many pixels per inch would be a fun problem to have, and I can tell you that in my 15 years, I feel old. My 15 years in the industry, I am yet to run into an image that's too large. Although I did see a student do it once, but that's mostly because they repeated an image. There was a student in our class once who did a step and repeat and multi-upped a bunch of stickers he was going to print onto one sheet in Illustrator, and he ganged it up for our large format printer, the one that can print feet wide by feet long on a giant roll of paper, and he put hundreds of this sticker onto one image. And the actual image size was multiple gigabytes, and he shut down, kind of locked down, broke a computer, froze it for the day, trying to show us that image on the screen. So it is possible to have too many pixels per inch. If you have too much image, you end up with the computer not able to handle it. Although in the wild, I've never run into this, only in the laboratory. So if you don't have enough resolution, the picture on the left here is low resolution. It's jagged or blurry. One of the things you might notice is things don't really get blurry anymore or jagged anymore. Instead, they get blurry because of something called anti-aliasing, where computer images automatically blur the edges so you don't see the jagged edges on your picture. This is fine. It's just to understand that you might not see the square edges so much as you see softer edges, but there's still no detail. The picture's not crisp at all. Meanwhile, if you get enough, just enough, the correct amount of resolution for your picture is what you're going for. Again, too much will lock down a system and freeze an output device. Too little will look bad. So you want to get right there in that Goldilocks middle zone. So the Nyquist theorem is something we'll end on probably for this video. Harry Nyquist was an electrical engineer who came up with this. He was trying to figure out how much electrical power you had to put behind a radio transmission to make sure it overcomes other background noises to be received on the other end. The same theory ends up being adapted to work for printing to help us determine our final image size when scaling images. Here it is at the bottom in red. LPI times 2 times percent. So the LPI is the lines per inch of your print, times 2 will get you the dots per inch of the screen, the computer screen resolution required, multiplied by the percentage of how much bigger or smaller it's going to be. So lines per inch is the number of halftone dots per inch, LPI. It's also known as line screen or screen ruling. Since we can't print shades of gray, we can only print yes ink or no ink, we approximate it by printing dots that are larger or smaller. Remember, bigger dots means darker colors, smaller dots means lighter colors. That's a halftone. When you output a pixel-based image, a raster image, to make a printing plate or even to run on a digital machine, it gets converted from pixels to halftones. And they simulate at a decent distance what continuous tones should look like while not being that. Pixels become dots. I really love this image, by the way. You have the grayscale image on the left, and that is turning into the black and white halftones on the right. A color image turns into 4 sets of halftones on top of each other, one for cyan, magenta, yellow, and black, respectively. Screen ruling. So this has to do with how many dots per inch your press is going to use. And more or less, you want to word falling out of my head. I'm sorry, guys. You want to match the needs of your paper and your ink and your press's capabilities in choosing one of these. So if you're printing something like newspapers, newsprint is notorious for something called dot gain, where small details disappear or just grow and get larger. So you kind of print with fewer dots to eliminate quite the same level of error you'd get if you tried to print high quality on a newspaper. It would look like mud. You just wouldn't get anything good out of it. 150 is normal for brochures and books and publications, and higher dots per inch for even better things. Think like your traditional National Geographic magazine has a much higher screen ruling than a newspaper because the images are so much clearer and the paper is so much nicer. The more porous your paper is, the more you need a coarser line screen. And you want 2 pixels per halftone dot. And you multiply that by the percent of the enlargement or reduction. So you get to the larger or smaller than what you're getting to is the number of dots needed. Now, we don't have to do these calculations by hand. This theorem and these calculations are a holdover from the days of when you had to use film and photographic lenses to do enlargements. You're basically shooting a picture of your picture through a screen ruling mesh and through an enlargement lens. It's basically a giant magnifier to make it bigger or smaller. So you had to know your percentages and everything before you started. Now you can just do this in Photoshop, and I've included a separate video here of a short demo of how to do that in Photoshop. All right, stay tuned till next time.